Deep beneath the nuclear power plant, a network of rigid concrete structures houses the facility's critical cooling pipes. During a major earthquake, these subterranean lifelines face massive tectonic forces, with thousands of tons of shifting soil and rock grinding directly against their walls. Standard highway tunnels are designed to weather an earthquake and simply stay open for traffic. The systems beneath a nuclear facility operate under different rules. A hairline fracture that admits groundwater or a slight bending that pinches a pipe can compromise the entire cooling network. For these structures, the tolerance for physical rupture is 0. Engineers cannot safely test these physical thresholds by waiting for a massive magnitude 8 earthquake to strike an active power plant. They have to prove these structures will hold through strict mathematics before the concrete is ever poured. Predicting how these underground systems react to a quake involves a specific sequenced pipeline of data processing. When analyzing how Earth interacts with structures, civil engineers frequently rely on two prominent simulation methods, the shake algorithm and the two-dimensional finite element method, known as FEM. A common misconception in the industry is that these two programs are competing alternatives. Modeling a massive seismic event using only one of these tools creates a mathematical blind spot. One program analyzes only the dirt. The other requires highly specific shaking data to analyze shapes. Neither works in isolation. Shake and 2D FEM are actually parts of a strict, non-overlapping sequential pipeline. The output calculation of the first is the required input data for the second. Treating these complex calculations as standalone solutions guarantees an incomplete picture of the physical stresses acting on a nuclear plant. Before simulating an earthquake, engineers must establish the baseline state of the ground. They map out the constant, everyday forces acting on the buried concrete, the heavy downward weight of the soil, static underground water pressure, and gravity. With the baseline set, Phase 1 begins using the shake algorithm. At this stage, the software explicitly ignores the concrete structure entirely. Its singular focus is calculating one-dimensional soil behavior from deep underground up to the surface. Engineers feed raw, theoretical bedrock earthquakes, massive design ground motions, labeled SS and SD, into the deep bedrock layer of the software. Here, the software calculates the Earth's filtering effect. As the theoretical earthquake travels up from the bedrock, soil layers alter the wave's shape and frequency. The result is the input wave, the exact vibration profile that will strike the construction site's bottom edge. Shake is a translator. It takes a theoretical global event and converts it into a precise, localized mathematical threat. That mathematical threat is then handed off to Phase 2, the two-dimensional finite element method. FEM's core computational role is to take the concrete box, the engineered backfill dirt, and the surrounding bedrock, and mathematically lock them together into a single interdependent system. In this combined cross-section, Shake's input wave is injected at the model's absolute bottom. As the wave forces upward, the software calculates the soil-structure interaction. FEM outputs highly specific stress measurements, the exact degree of concrete bending, joint stretching, and surrounding physical soil pressure. This 2D FEM phase proves exactly how the structure will physically deform under stress. It successfully turns abstract wave data into measurable forces. For a standard commercial building, sustaining those forces without collapsing is the ultimate metric of success. Nuclear engineering operates on a stricter standard, where simple structural survival is insufficient. This initiates Phase 3, the limit state check. This final phase shifts the engineering focus away from the structure's physical form and directly onto its required functionality. One vital metric is water tightness. Engineers evaluate the joint stretching calculated during the FEM phase to determine if the gap widened enough to allow groundwater to breach the system. Another metric is internal clearance. They evaluate the bending of the concrete walls to determine if the physical deformation would compress the interior space and crush the critical cooling pipes housed inside. This diagram illustrates the final step. The specific physical deformations calculated during the FEM phase are mapped directly to their corresponding functional failures. The limit state check determines if the structure can still perform its safety functions, even if the concrete has sustained measurable damage. This data pipeline, moving from 1D waves to 2D stress and finally to functional limits, provides the mathematical proof required for nuclear-grade safety guarantees.